Representations of functions as power series. Imagine trying to evaluate a complicated function like ln quantity 1 plus x without a calculator. What if you could write these functions as infinite polynomials that are easy to differentiate and integrate? For today's discussion, we are going to talk about representations of functions as power series. For our lesson objectives, by the end of this video, you will be able to define a power series, represent common functions as power series, and perform term-by-term differentiation and integration of power series. For our lesson outline, introduction to power series of convergence, the geometric series and its applications, step-by-step examples of rewriting functions as power series, differentiation and integration of power series, and final recap and assessment. By the way, what is power series? Power series is an infinite series of the form summation of Cn quantity x minus a raised to n that is approaches to 0 until infinity, where a is the center and Cn are the coefficients. For radius of convergence, it is the value such that the series converge when absolute value of x minus a is less than r. And geometric series is a function 1 over 1 minus x is equal to the summation of x raised to n approaches to 0 until infinity, wherein the absolute value of x is less than 1. James Gregory and Isaac Newton were among the first to explore infinite series for trigonometric and logarithmic functions, leading to early developments in calculus.
Okay, let's have our example number 1. Express 1 divided by 1 plus x squared as the sum of a power series and find the interval of convergence. Since it is a geometric series, we can use the general formula 1 all over 1 minus x is equal to the summation of x raised to n, where n is equal to 0 approaches infinity, and the absolute value of x is less than 1. Therefore, we may now replace x by negative x squared. Now, we can write 1 divided by 1 plus x squared is equal to 1 divided by 1 minus the quantity negative x squared is equal to the summation of the quantity negative x squared raised to n, which n approaches 0 raised to infinity, is equal to the summation of negative 1 raised to n times x raised to 2n, which n approaches 0 to infinity, where the absolute value of x is less than 1. Therefore, 1 divided by 1 plus x squared is equal to a series 1 minus x squared plus x raised to 4 minus x raised to 6 plus x raised to 8, and if we continue it, it approaches infinity. Now, let's test its convergence. Let a sub n is equal to negative 1 raised to n times x raised to 2n. Therefore, the limit of absolute value a sub n plus 1 divided by a sub n, which n approaches infinity, is equal to the limit of the absolute value x raised to 2 times the quantity n plus 1 divided by x raised to 2n, where n approaches infinity, is equal to the absolute value x squared. Therefore, the geometric series converge if and only if the absolute value of x squared is less than 1. And we can now get its interval of convergence as negative 1 and 1. Let's try our second example. Find a power series representation for ln 1 plus x, and its radius of convergence. Since it is a function, we can use our L'Hopital's rule, where we can get its derivative, and its derivative is equal to 1 divided by 1 plus x. Therefore, we can get now a geometric series like 1 divided by 1 plus x is equal to 1 divided by 1 minus the quantity negative x is equal to a series 1 minus x plus x squared minus x cubed plus, if we continue it, it approaches infinity, where the absolute value of x is less than 1. Integrating both sides of this equation, we can get ln 1 plus x is equal to the integral of 1 divided by 1 plus x is equal to the integral of the quantity 1 minus x plus x squared minus x cubed plus infinity is equal to x minus x squared divided by 2 plus x cubed divided by 3 minus x raised to 4 divided by 4 plus infinity plus constant. And we can write it as the summation of negative 1 raised to n minus 1 times x raised to n divided by n plus c, where n approaches 1 to infinity, and the absolute value of x is less than 1. To determine the value of c, we let x is equal to 0 in this equation, and we can get ln 1 plus 0 is equal to c. Thus, c is equal to 0 and ln 1 plus x is equal to x minus x squared divided by 2 plus x cubed divided by 3 plus x raised to 4 divided by 4 plus infinity is equal to the summation of negative 1 raised to n minus 1 times x raised to n divided by n, where n approaches 1 to infinity and the absolute value of x is less than 1. Since ln 1 plus x is also equal to a geometric series 1 divided by 1 plus x, and a geometric series has its radius of convergence of 1, therefore, we can conclude that the radius of convergence of ln 1 plus x is also equal to 1.
Okay, for example number 3, we express 1 all over the quantity 1 minus x raised to 2 as a power series by differentiating equation 1. What is the radius of convergence? First, we differentiate each sides of the equation, where 1 all over 1 minus x is equal to 1 plus x squared plus x cubed plus to infinity is equal to the summation of x raised to n, where n approaches from 0 to infinity. We get 1 all over the quantity 1 minus x raised to 2 is equal to 1 plus 2x plus 3x raised to 2 plus until infinity is equal to the summation of n times x raised to n minus 1, where n approaches from 1 to infinity. If we wish, we can replace n by n plus 1 and write the answer as 1 all over the quantity 1 minus x raised to 2 is equal to the summation of the quantity n plus 1 times x raised to n, where n approaches from 0 to infinity. So according to theorem number 2, the radius of convergence of the differentiated series is the same as the radius of convergence of the original series, namely r is equal to 1. Our takeaways for our today's topic about representation of functions as power series. First, power series can represent many standard functions. Next, the radius of convergence is key in understanding where the series is valid. Term by term, differentiation and integration are powerful tools for solving calculus. And lastly, these methods are not just theoretical, they are used in physics, engineering, and computer science. You may try this. For the problem number 1, express the function 1 all over the quantity 1 minus x raised to 2 as a power series and find its radius. And problem number 2, find a power series representation for the f of x is equal to tan raised to the negative 1 times x.